Okay, get ready for a wild ride because we are diving headfirst into the world of non-commutative algebra.
That's right, where the rules of math get well, a little weird.
To say the least, today we're tackling this,
This beast.
yeah, this beast of a research paper called Descent and Generation for Non-Commutative Coherent Algebras over Schemes.
Oh, catchy title.
Very catchy, very catchy.
But don't worry, you're going to break it down into digestible pieces for you.
Exactly, because our mission, should we choose to accept it, is to help you understand how shapes and structures behave.
Or maybe misbehave.
Or misbehave. I like that when we just completely flip the script on the usual rules of multiplication.
Yeah, imagine a world where you multiply two numbers and you get a completely different answer depending on the order you multiply them in.
Mind-blowing, right?
Yeah.
So to kick things off, let's set the stage. What exactly are we talking about when we say non-commutative algebra?
So at its heart, it's all about these spaces, these mathematical spaces, where the usual rules of combination just don't apply.
We're talking addition, multiplication, the whole shebang.
The whole shebang. And these spaces, they're called non-commutative schemes. And they're way more connected to our everyday world than you might think.
Okay, now you've got me intrigued.
All right, so let's take computer graphics, for example.
Right.
You know those incredible special effects you see in movies? Or how about those amazingly realistic video games?
Oh, yeah.
Well, a lot of that relies on understanding how shapes and objects behave in these kind of wonky spaces.
So we're talking like the crazy world of CGI and animation.
Exactly. It's all about manipulating and transforming these shapes in ways that our regular geometry just can't handle.
Wow, so like those epic lightsaber battles in Star Wars could actually be secretly powered by non-commutative algebra.
You could say that.
That's amazing.
It's more than just lightsabers, though. This kind of math pops up in cryptography.
Okay.
Where keeping information secret depends on scrambling things up in just the right way.
Right, right.
And even in quantum physics, where the rules of reality get really, really strange.
It's incredible how these seemingly abstract mathematical concepts can have such tangible implications in the real world.
Yeah, math is everywhere once you start looking for it.
Now, this research paper we're diving into focuses on two key concepts: generation and descent.
Two big ideas.
Two big ideas.
Yeah.
So let's start with generation. What's that all about?
Okay, so imagine you have this giant complex Lego structure. We're talking thousands of pieces, maybe even millions, right?
Okay, I'm picturing it.
And your task is to figure out the absolute minimum number of unique Lego blocks you would need to build that entire structure.
So it's like finding the most basic building block.
Exactly, the essential ingredients that make up this complex thing.
Okay, so in the context of this paper, what are those essential ingredients, those building blocks of these non-commutative spaces?
So what these researchers found is that in these non-commutative spaces, the fundamental building blocks are something called sheaves of ideals.
Sheaves of ideals, that sounds a little more complicated than snapping together Legos.
Well, yeah, a bit more abstract, sure.
Okay, so we've got these sheaves of ideals as our building blocks, but how do we actually start putting them together to make sense of these complex spaces? And that, I'm guessing, is where descent comes in.
You got it. Descent is all about breaking down these complex mathematical structures into smaller, more manageable pieces.
Kind of like taking apart a clock to understand how all the gears and springs work together.
Yeah, that's a good way to put it.
So it's like we're trying to understand how this entire intricate machine works by examining its individual parts.
Exactly. We zoom in, study how those individual pieces behave, and then try to piece together the bigger picture.
It's like having a map of a vast, uncharted territory. Generation gives us the key landmarks, while descent helps us navigate the intricate network of paths connecting them.
I like that analogy. It's all about seeing how the local and global fit together, how those individual pieces contribute to the overall structure.
This is where my brain starts to get really excited.
Got it, good, yeah.
Because then they bring up this whole other concept, Azumaya Algebras. What makes these algebras so special?
So Azumaya Algebras are fascinating because they're kind of like chameleons in the world of math.
The chameleons, okay.
Locally, they look and behave like matrices.
Matrices, like the stuff we learned in high school.
Yeah, exactly. Those rows and columns of numbers. And matrices are well understood. We've been studying them for centuries.
Okay.
So this ability for Azumaya algebras to mimic matrices in certain situations gives mathematicians this really powerful tool to analyze them.
So it's almost like having a Rosetta Stone that helps us translate between the familiar world of matrices and the more exotic realm of these non-commutative Azumaya algebras.
Exactly. And anytime you can find those kind of connections between different areas of math, Yeah, you're onto something interesting.
Now, speaking of interesting things, this research takes us on a detour into a particularly mind-bending concept, prime characteristic. What is that all about?
Okay, so imagine a world where the rules of arithmetic are just slightly different, where prime numbers are even more fundamental than they are in our usual number system.
So it's like we're stepping into an alternate mathematical reality.
You got it.
Okay, now I'm really intrigued. Why explore non-commutative algebra in this strange new world of prime characteristic? What's the point?
Well, sometimes stepping outside the familiar can reveal hidden patterns and connections that we might have missed otherwise.
Oh,
It's
yeah.
like those aha moments you get when you look at a problem from a totally new perspective.
So it's like prime characteristic gives us a new lens through which to examine these mathematical structures, potentially revealing hidden truths and deeper insights.
Absolutely. It's all about pushing the boundaries of our mathematical understanding and seeing what we can discover in the unknown.
Well, I'm already hooked, and we've only just begun to scratch the surface. This is shaping up to be a wild ride through the fascinating world of non-commutative algebra. But before we get too far ahead of ourselves, let's take a moment to unpack some of these concepts a bit further.
Yeah, it's kind of like we've given you a quick tour of a vast and intricate jungle. Now let's grab our machetes and delve a bit deeper into some of the denser parts.
I'm game if you are.
All right, let's do it.
So we left off talking about prime characteristics, that alternate reality where prime numbers are king.
Right.
What's so special about exploring non-commutative algebra in that strange new world?
Well, it turns out that in prime characteristic, things actually become clearer.
Clearer. How so?
It's like in this alternate reality, the math becomes cleaner, more elegant, allowing us to pinpoint the exact building blocks needed to generate certain types of Azumaya algebras.
So it's like prime characteristic simplifies things, revealing those fundamental building blocks that might be hidden in our usual mathematical world?
Exactly. And this simplification can lead to incredible insights. It's like suddenly understanding a complex machine because you've got the blueprint right in front of you.
I'm starting to see the appeal. Now, this research paper takes these ideas even further by looking at how this idea of generation, finding those building blocks, behaves under different conditions, different constraints. What did they find?
Well, they found that those fundamental building blocks, they're not static.
Mm.
They can change and interact in fascinating ways depending on the rules of the game.
So it's like observing how those Lego blocks we talked about earlier might behave differently if you suddenly change the laws of physics.
Exactly. Like what happens if we play Lego underwater or in zero gravity? Do the blocks still connect in the same way? Do we need different types of blocks?
So they're basically stress testing these mathematical concepts, pushing them to their limits to see what happens.
Precisely. And one of the tools they use to do this is something called the H topology.
H topology. Okay, that one sounds a bit intimidating. Can you break that down for us?
Okay, imagine you're trying to get around a city.
Hmm.
The usual way we think about distance is like how many miles or kilometers it takes to get from point A to point B, right?
Right.
But the H topology is like saying, forget actual distance, let's just think about how well connected things are.
So, like, two neighborhoods might be geographically far apart, but they're considered close in the H topology if there's a direct subway line connecting them.
Exactly. It's about considering different types of proximity, different ways of measuring closeness.
Yeah.
And what's fascinating is that even when you look at these non-commutative spaces through the lens of the H topology, this whole idea of generation still holds up. You can still find those fundamental building blocks.
So it's like finding a universal language that transcends these specific conditions, speaking to a deeper truth about these mathematical structures.
You're getting it. It's like discovering a hidden code, a blueprint that underpins all these different variations.
Now, we've talked about generation and descent, but this research delves into another concept that sounds even more mind-boggling. Countable Rouquier dimension.
Okay, yeah, that one's a mouthful.
It is a mouthful. What is that all about?
So imagine you're trying to build something really complex, like a giant, intricate sculpture or an incredibly detailed piece of machinery, right? Countable Rouquier dimension is a way of measuring how many steps it would take to build that thing, but with a catch.
Okay, there's a catch. There's always a catch.
Right. You're only allowed to use a very specific set of tools, a limited toolbox.
So it's like a measure of complexity, but with a constraint on the resources you can use to create that complexity.
Exactly. It's like saying, okay, you can build anything you want, but you only get to use these 10 Lego blocks.
Okay, I see. So how does this countable Rouquier dimension play out when we're talking about those complex Azumaya algebras?
What's fascinating is that even for these Azumaya algebras, which we know can get really wild and complicated, The countable Rouquier dimension can be surprisingly low, especially when you're working in these special types of spaces called derived splinters.
Derived splinters. Okay, you're going to have to help me out with that one.
All right, so imagine a perfectly smooth piece of glass, no cracks, no imperfections. That's kind of like a derived splinter in this context.
So they're like the ideal spaces, mathematically speaking.
You could say that. They have these really nice properties that make them easy to work with, mathematically speaking. Kind of like if you're building something out of Lego, it's a lot easier to do it on a smooth, flat table than on a bumpy, uneven surface.
That makes sense.
Yeah.
So even though Azumaya algebras can be super complex, as long as they're operating within these pristine derived splinter spaces, they become more manageable.
Exactly. And that's one of the key things these researchers found. Even when we're dealing with these super abstract, mind-bogglingly complex mathematical objects, there's still a sense of order, of predictability in how they behave.
It's like finding patterns in the chaos.
Precisely. There's a certain beauty in that, don't you think? This search for patterns, for order, in the midst of all this complexity.
I agree. It's quite remarkable. Now, earlier we were talking about how exploring non-commutative algebra in that strange world of prime characteristics can sometimes simplify things.
Right. Prime character.
Exactly. So where does that idea fit into all of this? What's the connection? It's like we're trying to piece together a giant jigsaw puzzle, and we just found a few more pieces that fit.
And with each new connection we make, the bigger picture starts to come into focus.
Exactly. So we were talking about how prime characteristic can sometimes simplify these complex Azumaya algebras, right?
Right.
But it goes even deeper than that. It turns out that this connection to prime characteristic has some pretty profound implications for a whole other area of math, algebraic geometry.
Yeah, algebraic geometry, that beautiful marriage of algebra and geometry.
Okay, I have to admit, whenever I hear algebraic geometry, my brain goes a little fuzzy. Can you give us a quick refresher on what that is and why this connection to prime characteristics is so significant?
So imagine you're not just picturing shapes in your head, you're also thinking about the equations that describe those shapes.
Okay, so like a circle isn't just a circle, it's also the equation x squared plus y squared equals some constant.
Exactly.
Ah.
Algebraic geometry is all about that interplay between the visual world of shapes and the symbolic world of equations.
Okay, I'm starting to see the connection. But how does prime characteristic fit into all of this?
Well, it turns out that when you study those equations in the world of prime characteristic, you start to notice things you might have missed otherwise.
What kind of things?
You start to see hidden symmetries, unexpected relationships between different geometric objects. It's like prime characteristic acts as this kind of special lens that reveals the deeper structure of these equations, and by extension, the deeper structure of the geometric shapes they represent.
So by exploring Azumaya algebras and prime characteristic, we're actually gaining a deeper understanding of geometry itself.
Precisely. It's like we're cracking a code, unlocking hidden meanings within the very fabric of shapes.
It's incredible how these seemingly abstract mathematical concepts like prime numbers can have such a profound impact on our understanding of something as fundamental as geometry.
That's the beauty of math, isn't it? It's full of these surprising connections, these beautiful, intricate patterns that connect seemingly unrelated ideas.
It really is. Now, I know we're running out of time, but before we wrap up, I'm curious, were there any particular findings in this research that you found especially intriguing or that you think could lead to exciting new avenues of exploration?
You know, there's one thing that really caught my eye. Towards the end of the paper, they briefly mentioned something called the ANC8 Frobenius morphism.
Okay, I have to admit, that sounds a little intimidating.
It is a bit of a mouthful, but essentially it's like they've uncovered this hidden passageway, this potential shortcut within this vast mathematical landscape.
A shortcut. Tell me more.
Now, they only touch on it briefly, but it hints at a whole new set of connections, a new way of looking at these non-commutative spaces.
It's like they're leaving us with a cliffhanger.
Exactly. They've given us a glimpse of something truly remarkable, and now it's up to other mathematicians to pick up the torch and explore this new territory.
Well, I think it's safe to say that our brains are officially fried.
In a good way, I hope.
Absolutely in a good way. This deep dive into the world of non-commutative algebra has been a wild ride, full of twists, turns, and those aha moments that make you appreciate the power and beauty of mathematics.
I couldn't agree more.
And to our listeners, we hope you've enjoyed this journey as much as we have. Remember, the world of mathematics is full of surprises, so keep exploring, keep asking those big questions, and who knows what incredible discoveries you might uncover. Until next time. Hey everyone, welcome back. Ready to dive into something a little different today.
Different is good, right?
Absolutely. Though I'll admit this one sounds pretty intense even for us. We're tackling non-commutative coherent algebras over schemes.
Definitely a mouthful.
But that's why we're here, right? To break it down, we've got this research paper, and let me tell you, the title had me reaching for a math dictionary.
The title's definitely a bit dense, yeah, but the ideas underneath are really cool when you get past the jargon.
Okay, so you're saying there's hope for us non-math geniuses.
Absolutely. What's fascinating here is it connects to how we understand geometry, which everyone can wrap their heads around.
Okay, I'm intrigued, but we got to start with the basics. What in the world are we talking about with non-commutative coherent algebras over schemes?
All right, so imagine a perfectly ordered city grid, right? Streets meet at right angles, everything's predictable, that's your regular scheme.
Got it, like a nice, neat blueprint.
Exactly. But now picture adding buildings with weird shapes, skywalks connecting them, underground tunnels. It's still structured, but way more complex.
Okay, so our nice grid just got a whole lot more interesting.
Right. And the usual rules don't quite apply anymore. That's what we're getting at with non-commutative states. How things combine isn't straightforward.
So it's like our city grid got a serious makeover, and we're trying to make sense of the new layout.
Exactly. And just like we use blueprints for buildings, mathematicians look for the building blocks of these non-commutative structures. Those are called generators.
So generators are like figuring out the essential elements, the DNA almost, of our strange non-commutative city. Why is that so important?
It's all about understanding what these complex systems are made of at their core. The paper dives into different levels of generators. Classical, strong germ generator. Think of it like ranking how good they are at building different parts of our city.
So some are like multi-tools, others are more specialized.
That's a great way to put it.
And this paper actually gives us some real-world examples of these in action.
Absolutely. Examples 2.4 and 3.18 show how these different types have been used to solve problems, like using different tools to build our city.
This is already making more sense. We've got our weird city, the blueprints, the tools. But where does coherent fit into all of this? What makes these algebras coherent in this context?
Good question. Coherent here refers to a specific set of rules these algebras follow. Think of it like zoning laws in our city. They might seem limiting, but they provide a framework.
So even though our city is non-commutative, those coherence conditions provide some sense of order.
You got it. And those rules are powerful. They allow mathematicians to prove some amazing things about these non-commutative spaces. This is where descent comes in.
Descent. Okay, now you're making me think of exploring the underground levels of our city, like some hidden tunnels and connections.
I like that analogy. Imagine wanting to understand our whole city, right? Instead of going everywhere, you choose key areas: downtown, suburbs, industrial zone.
And if you understand those, you get a sense for the whole city.
Precisely.
Yeah.
That's descent, breaking things down into manageable pieces. The paper uses the H topology as a tool, almost like a mathematical zoom lens.
So it's working smarter, not harder. Instead of every building, we find these key areas that unlock the whole structure.
Exactly. And that's just the beginning. It's really cool, actually, this H topology. It's like if our city was a photograph, this lets us zoom in on different neighborhoods.
Okay, so we're not just stuck with one view of the city anymore.
Right. And each view, each covering, lets mathematicians look at problems in new ways, so we get a much better understanding of these non-commutative spaces.
I like it. So we've zoomed in with our mathematical lens, we've got descent figured out, but the outline also mentioned lifting. Where does that fit in our city exploration?
Good point. Imagine you build a miniature model of our city, all the quirks and all.
A tiny non-commutative city. I love it.
Exactly. Now, lifting asks, if something's true in the model, can we apply it to the full-size version?
So whatever we prove in our mini-city could be lifted to the real deal.
That's the idea. It's like a blueprint, right? Study the small one, learn about the big one. In the paper, they use proper morphisms, which are like maps connecting our spaces, but they preserve certain properties so we can transfer knowledge like that.
This is blowing my mind a little, finding connections all over our non-commutative city. But okay, with all this complex stuff, are there any actual uses for this research? Or is it still theoretical?
That is the question, right? And it's funny, it's kind of both. This paper is deep into the math, but it could actually affect things like, get this, cryptography.
Now you're speaking my language. Cryptography, always cool. Tell me more about this connection.
Remember prime characteristic, like that hidden code in our city's design.
Yeah, it kind of determines how the whole thing's built, right?
Exactly. Turns out, That's huge E in cryptography for how strong encryption is, how secure everything stays.
So our non-commutative city, it's got good security thanks to prime characteristic.
In a way, yeah. The paper looks at Azumaya Algebras. Remember those? The well-behaved zones.
Our nice quiet neighborhoods, yeah.
Right. Those connect directly to this prime characteristic idea. Gives us a better understanding of how it affects everything.
This is getting juicy. Like, we're figuring out the security system built into our city.
And it gets better. The paper even talks about how, by understanding Azumaya algebras through this prime characteristic lens, we might make cryptography better.
Okay, hold up. Got to make sure I'm following. So abstract math leads to more secure data.
It's wild, right?
Yeah.
But before we get too far into that, let's talk about stock local information. Ever heard of that?
Can't say that I have. Sounds like we're about to get really granular with our city exploration.
You know it. Imagine wanting to know what a cake tastes like, right? You wouldn't just look at the frosting.
You got to pry all the layers.
Exactly. Stocks are like taking bites from different parts of the cake. They tell us about our non-commutative spaces piece by piece.
So instead of the whole city at once, we're trying each neighborhood, really getting the flavor.
That's the idea. And the paper shows that doing this, focusing on the stocks, can make it way easier to figure things out.
Sometimes the small stuff unlocks the big picture, huh?
You got it. And in math, those are the breakthroughs, seeing things in a whole new way.
Okay, love it. But how does this stock local idea connect back to our Azumaya algebras, our quiet zones?
That's a great question. It's like we're trying to understand the specific zoning laws of those quiet neighborhoods in our non-commutative city by tasting different pastries from each bakery. Exactly. The paper shows this stock local approach is especially helpful with Azumaya algebras. Analyzing those stocks helps us get what their structure is, how they work with the rest of that non-commutative stuff around them.
So each stock is like a peek into how those well-behaved zones stay so orderly amidst all the chaos.
You got it. And this lets mathematicians prove some really cool things about Azumaya algebras. Like, the paper uses this to prove a non-commutative version of a really important algebra result. It's like finding a secret link between how our quiet neighborhoods are built and some law of physics that runs the whole city.
Now that's a discovery. Seems like this paper's full of hidden connections in math, huh?
For sure. And it shows what's so great about math research. A lot of times, the biggest aha moments come from finding these unexpected links, seeing things in totally new ways.
Totally agree. But we've been talking about cryptography. How does all this, the Azumaya algebras, the stock local stuff, how does that actually get used in the real world?
Right. So remember how we said prime characteristic was like a code in the city shaping how it's all put together?
Yeah, like the city's security system, kind of.
Exactly. Well, prime numbers, they're huge GE in actual cryptography for keeping data safe, making sure everything's locked down tight.
Makes sense. So our non-commutative city, it's got a good security system thanks to prime characteristic.
You could say that. The paper's findings about Azumaya algebras, when we look at them with prime characteristic in mind, they give us new ideas for making even stronger cryptography.
Oh, interesting. Like upgrading the locks on those quiet neighborhoods, making the whole city safer.
Exactly. The paper shows how to use something called the Frobenius morphism to build what we call strong generators for certain Azumaya algebras. And those strong generators, they're the key to better security.
Okay, now that sounds pretty intense. What exactly is this Frobenius morphism? How does it work with everything else we've talked about?
Okay, so imagine a city map, right? But this map doesn't just show you where buildings are. It also shows you how strong their foundations are, what they're made of, every little detail that keeps them standing.
That's one detailed map.
Right. That's kind of what the Frobenius morphism does. It lets us look at the stock local info. Remember those tasty bites of our city? It lets us analyze them to find those crucial, strong generators to make our cryptography super strong.
So by understanding those little details, those stocks, and then using this Frobenius morphism to really analyze them, that's how we end up with better security for our data.
Exactly. It's like reinforcing those quiet neighborhoods, making them even more resilient because they're so vital to how the whole city works.
Wow, that's pretty incredible. We started with what seemed like a really abstract mathematical idea and ended up talking about cryptography, data security, how it all impacts our digital lives.
It just goes to show you never know where math will lead, right? Sometimes the most theoretical stuff has these huge real-world implications. It's all about making connections and asking questions.
Couldn't have said it better myself. And on that note, we've reached the end of our deep dive into Non-commutative coherent algebras over schemes. We hope you enjoyed it as much as we did. Until next time, keep exploring, keep those questions coming, and keep your brains buzzing.
Okay, are you ready to dive deep into some seriously cool math with us today? We're taking on this research paper, and the title is a mouthful, but don't worry, we'll break it down. It's called Descent and Generation for Non-Commutative Coherent Algebras over Schemes.
Yeah, it's definitely a mouthful, but once you get past the title, the ideas inside are really fascinating.
That's what we're here for.
Mhm.
We're going to try to uncover some surprising connections in this paper, like between abstract algebra and geometry, the kind of geometry you might actually remember from school.
It's like finding hidden patterns, where things seem totally random at first.
I love that. Okay, so let's start with non-commutative. It's right
Right.
there in the title. Seems important.
It is. It's actually a pretty simple idea. Think about it this way. Imagine getting dressed, in the morning. Doesn't matter if you grab your phone first or your keys, right?
Right.
Those actions, that's what we call commutative. The order doesn't really change anything, but what about putting on shoes before your socks?
Okay, now you're just messing with me.
Uh-huh. No, but seriously, try it. It just doesn't work, right?
Definitely not.
Exactly. And that's because those actions are non-commutative. The order you do them absolutely changes the result. And this paper basically asks, what happens when you apply that same order matters idea to like how we understand math structures?
So we're not talking about shoes and socks anymore. We're talking about, like, equations and shapes and how the order we put them together changes the math we get.
Exactly. And this paper is really focused on how these non-commutative ideas work in a special area of math. It's called triangulated categories.
Okay, that sounds a little complicated.
It might sound complicated, but think of it like organizing information. Like imagine you have a ton of information to sort through. You might put things into categories, right? See how those categories connect to each other and then break them down into smaller, more basic parts.
So kind of like organizing a research project. You got your main topics, subtopics, all those little details.
Exactly. That's a great way to think about it. Mathematicians use these triangulated categories to understand these complex relationships by, finding the fundamental building blocks. And the twist here is that those building blocks are non-commutative, meaning that order. Super important.
Okay, so we've got these non-commutative things,
Mm-hmm.
and we're using these triangulated categories to organize them. But what about schemes? That word's in the title too. What are those?
Good question. In this paper, schemes, they're like the environment, the space where everything's happening. Think about building with Legos. You've got all these different bricks, but you can use them to build, well, anything, right?
So the scheme is like the base plate. It kind of sets the boundaries of what we're working with, and then the non-commutative part that tells us the rules for how we can connect those pieces.
That's a great way to put it. And this paper, what it does is it shows us this really cool shortcut for figuring out what we can build in this non-commutative Lego world.
Okay, a shortcut. You've got my attention. Especially when we're talking about complex math. But before we get into that, I mean, why should we even care? What's the point of building these structures? Like, what are the real-world applications here?
Well, the cool thing is that what we find out in these abstract areas of math often ends up being applicable to very real situations. The paper mentions these algebrogeometric consequences.
Okay, sounds intense.
Yeah, it's a bit of a mouthful. But basically, it just means that understanding these structures in math, it could help us understand how things work in the real world.
Okay, that sounds pretty cool, actually. Got any examples?
Well, one area where this research might be helpful is in understanding singularities.
Singularity.
Yeah. Have you ever, noticed a flaw in a material? Say, a crack in metal?
Sure. Happens all the time.
Or even something like a black hole way out in space, where the normal rules of physics, they kind of break down. Those are actually both examples of singularities.
Points where things just behave differently than we expect.
Yes, exactly. And by using these, studying these non-commutative structures, we just might, be able to understand these strange phenomena a bit better.
So this isn't just some purely theoretical math, then. It could actually have applications in things like, I don't know, material science, even astrophysics.
Yeah, exactly. It's pretty amazing. And it goes even further than that, though. These insights, they could also help improve things like supply chains, make computer algorithms more efficient even.
Wow. That's pretty impressive. It's amazing to me how something so abstract can have such a tangible impact. Okay, I'm definitely hooked. Now, you mentioned a shortcut this paper uncovers. Tell me more.
Well, it all starts with this idea of descent.
Descent. Okay.
Is a really powerful concept in mathematics. Basically, descent lets us understand something really complex by studying its smaller parts.
Break it down into manageable pieces.
Exactly. It's like if you wanted to understand a whole city, you wouldn't start by trying to explore every single street and building. You might start by focusing on a few key neighborhoods, right?
That makes sense.
And by understanding those neighborhoods, you could start to get a sense of how the whole city fits together. And that's kind of what descent allows us to do with math.
Okay, that makes sense. So how does this descent idea apply to the stuff in the paper? I mean, it seems like it could be really useful for understanding these non-commutative structures.
Yeah, and it is. The paper shows this with something they call Proposition A. Let's go back to the Legos for a second. Imagine you have a ton of Legos, right? And you want to build something specific. But you need to know if you have the right pieces. Instead of searching through every single brick, what if you could just look for a special type of block, like a strong generator, in a few small sections of your pile?
And if we find those special blocks, those strong generators.
That's what Proposition A is all about. It says that if you find those strong generators in just a few parts of your non-commutative scheme, you've basically found a strong generator for the whole thing.
Wow, that's a pretty big shortcut.
Yeah, it really is. It means you don't need to analyze every tiny detail to figure out how it's all connected.
This is amazing. So this idea of descent, it's all about finding those shortcuts, those principles that make even the most complex things, well, less complex.
You got it. And what's even cooler is this paper shows that these principles, they hold true even when you look at these non-commutative structures in different ways. We call these different perspectives topologies. It's like using different magnifying glasses to look at the same thing.
Oh, different perspectives. Now we're talking. But before we get ahead of ourselves, we'll save that for part 2.
Yeah, like in math, there are often so many different ways to look at the same thing, and each one can kind of give you a different piece of the puzzle.
I like that. It's like having different tools.
Yeah.
You need more than just that magnifying glass to solve a case.
Exactly. And so this paper looks at two specific perspectives, or topologies. That's what mathematicians call them. They're called FPPF and H topologies.
Okay. Those definitely sound a little technical.
Yeah, they do. But you can just think about them like different lenses, Like we're examining this non-commutative structure.
Okay, different lenses, but same goal, right? We're trying to understand these structures, but what does looking through these different lenses actually do?
Remember those strong generators we were talking about?
Yeah.
Well, the paper shows that even when you use these different lenses, they're still the key to understanding how it all fits together.
So no matter how we look at it, those strong generators are still like the foundation.
It really speaks to this underlying order and elegance in math,
I love that. Okay, so we've got descent, we've got different topologies. What other mathematical tools is this paper bringing to the table?
Well, they also dive into something called lifting generation with proper push forwards.
Okay, that one definitely sounds a bit intimidating.
It might sound complicated, but it's actually a pretty intuitive idea. Imagine you have a blueprint for a building, right? That blueprint, it's got all the information about the structure, but it's obviously on a much smaller scale than the actual building.
Right, it's like a representation.
Exactly. So in this scenario, the blueprint is like what we call a pullback. It's a way of taking all the important stuff about our non-commutative structure and putting it into a simpler form. And then there's the actual construction process, the push forward. That's where we take the blueprint and actually build the structure.
Okay, I think I see where you're going with this.
Yeah.
So we've got the plans and the actual building process. What does this paper say about the pullbacks and push forwards?
Well, they found that sometimes if you can find a strong generator for the smaller pulled back version of your structure, you can actually use that same information to understand the bigger picture, the pushed forward version.
So it's like if you understand the blueprint, you can figure out the whole building.
Yeah, exactly. It's all about taking what we know, even if it seems small, and using it to understand something much bigger.
That's so cool. Like in those detective shows where they find a tiny little clue and suddenly they can solve the whole mystery.
Exactly. It's recognizing how important those little details are. And speaking of small details, this paper also explores this really fascinating concept called stocks.
Stocks. Okay, now I think you're messing with me.
No. Haha. No, seriously, stocks are a real thing.
All right, I'm all ears. What are these mathematical stocks?
So imagine a stock as this tiny, tiny point in our non-commutative structure. It's almost insignificant on its own, but
But it's the key to the whole thing.
yeah, you got it. What this paper basically found is that if you understand what's happening at these tiny stalk levels, you can actually understand the entire structure sometimes. It's kind of like that idea that like a grain of sand contains a whole universe.
Yeah, that's a really cool way to think about it.
Hmm.
Okay, so we've got descent topologies, lifting generation, and now stalks. This paper is like a highlight reel of crazy math concepts.
And we're not done yet. This paper goes even deeper. It doesn't just talk about these general principles. It actually gets into the weeds with a specific type of non-commutative structure called an Azumaya algebra.
Azumaya Algebras. Okay, that sounds serious.
They're kind of like the VIPs of the non-commutative world. They're special because they have these properties that make them easier to work with than some of the others.
So they're like the model citizens of the non-commutative world. We can study them to learn about how the whole system works.
Exactly. And the really cool thing is this paper shows that even though Azumaya algebras are a bit more manageable, we can still use all those cool concepts like strong generators to understand them. It's like realizing that the same rules of physics apply to planets and pebbles.
That's a good point. Like it's
Um,
showing us there's this common thread that ties it all together.
Exactly. And the paper gets even more granular. It shows how we can actually measure the complexity of these Azumaya algebras using something called countable Rouquier dimension.
Okay, I'm not even going to try to pronounce that one. But measuring the complexity, that sounds interesting. What does that even mean in this context?
Think about it like building with Legos again. Some things are super simple to build, and some things take way more steps in planning.
Like a simple cube versus the Millennium Falcon.
Exactly. That's a good one. So countable Rouquier dimension, it's basically a way of measuring how hard it is to build different Azumaya algebras. And this paper shows that even though they can get really complex, they're still manageable, even when the scheme they're on is more complicated.
So even though it's complex, there's still some order to it.
Yeah, you got it. And that's what's so exciting about this research. It's not about getting lost in how complicated things can be. It's about finding those patterns and shortcuts that make it all make sense. And believe it or not, all of this exploration of these non-commutative structures actually leads us to a pretty surprising place: prime numbers.
Prime numbers. Now we're going down the rabbit hole. I thought we were talking about algebra and geometry, not like the building blocks of numbers.
It does seem like a jump, but trust me, these things are more connected than you might think.
Okay, you've definitely got my attention. Bring on the prime numbers.
Yeah.
Prime numbers.
Yeah.
All right, you've got to connect the dots for me here. How do prime numbers fit into all of this non-commutative stuff we've been talking about?
Well, remember how we were saying schemes are like the playing field for all of this?
Right, like the base plate for our Legos?
Exactly. So there's this special type of scheme called an F-finite scheme, and these guys, they're really connected to prime numbers.
Okay, so F-finite schemes are like the bridge between this non-commutative world and prime numbers.
You got it. And what's really wild is that this paper shows that even when we're working with these F-finite schemes, these prime number-related things, we can still use the idea of strong generators.
So no matter how deep we go, those strong generators are still the key.
It's amazing, right? This paper really shows how powerful that idea is. And one of the coolest examples of this is something the researchers call Theorem G.
Theorem G. All right, what's so special about that one?
Well, Theorem G basically gives us a set of instructions for finding those strong generators in these F-finite situations.
So it's like we had this general map for navigating this whole world of non-commutative structures. And Theorem G is giving us like a detailed route for a very specific area.
Perfect analogy. It's like we're zooming in from the big picture to a tiny little neighborhood and seeing how it all works on a smaller scale.
Wow, that's amazing. Okay, so we've covered a lot. We've gone from non-commutative socks and shoes to blueprints and now even prime numbers. What's the big takeaway? What do you want our listener to remember from all of this?
I think the biggest thing is just how powerful mathematical thinking can be. It helps us find these incredible patterns and shortcuts, even when things seem impossibly complex. And it shows us how everything is connected, even things as different as algebra and geometry.
It's like we've gotten a glimpse behind the scenes of how math works, you know?
Exactly. And like with any good discovery, this research leaves us with even more questions. In fact, the paper ends with this really interesting thought about something called, get ready for it, non-commutative Frobenius morphisms.
Non-commutative Frobenius morphisms. You're just making stuff up now.
It does sound made up, doesn't it? But without getting too technical, it basically suggests there's a whole other level of complexity to these non-commutative structures.
So it's like this paper isn't just the end of the story, it's just the beginning.
Exactly, and that's what makes math so amazing. It's a journey of discovery that never really ends.
Well said. And who knows what other patterns and connections are out there, just waiting for someone to find them. This is The Deep Dive, signing off.
Ever feel like high school math kind of left you unprepared for all the really advanced stuff?
Uh-huh, yeah, I know what you mean.
Well, today we're diving into a paper that might seem pretty intimidating.
Mm-hmm.
Descent and Generation for Non-Commutative Coherent Algebras over Schemes.
Catchy title.
You sent this in, so someone out there is ready to go deep on this, and
Hopefully by the end of this, they'll be glad they did.
that's the goal. So let's start with the absolute basics. What exactly is non-commutative algebra?
Okay, so you know how like when you add numbers, the order doesn't matter. Like 2 plus 3 is the same as 3 plus 2.
Right, basic addition.
Exactly. Commutative. But imagine a world where that's not always true, where the order you do things really changes the outcome.
Okay, starting to sound a little trippy.
That's non-commutative algebra in a nutshell.
So how on earth does that relate to geometry, which is what this paper seems to be about?
So this paper explores those order matters situations, but within the context of geometric shapes. It's like taking what we know about lines, curves, surfaces,
Right, familiar geometry stuff.
and then viewing them through this non-commutative lens, which can reveal hidden structures and relationships we wouldn't notice otherwise.
I see we're already starting to use some pretty dense terminology here. Skeins, sheaves. These aren't exactly words I throw around every day.
Right, right. So think of a scheme as a way mathematicians have found to generalize the idea of geometric spaces. Allows us to talk about shapes in a much broader, more abstract way.
So instead of just picturing like a circle on a piece of paper.
Yeah. It's more about the concept of a circle, but in a much more flexible way.
Got it. And then sheaves, those are our tools for actually working with those spaces.
Exactly. She's let us study those spaces locally, piece by piece. Imagine examining a globe, one continent at a time.
Okay, that makes sense.
That's kind of what a sheaf does for a scheme.
And then to make things even more interesting, we have these coherent algebras coming into play.
Right, so that's where things really start to get non-commutative. A coherent algebra over a scheme adds this extra layer of structure. It's like giving each point on our globe special properties, but these properties can interact in all sorts of non-commutative ways.
My brain is definitely starting to twist a little here, but I think I'm following so far. Now, the paper keeps mentioning generators. What role do generators play in all of this?
Okay, so imagine you have this massive Lego set, right? But instead of regular blocks, you have all these abstract mathematical objects. Finding generators is like discovering the most fundamental pieces in that set.
The ones you need to build anything else.
Exactly. They're the keys to unlocking the complexities of this non-commutative world.
So finding those generators is kind of like cracking a code. It lets you build anything you can imagine within this world.
Exactly. And in this paper, the researchers are really going after the master keys, the generators for these complex non-commutative spaces.
Yeah, that sounds like a seriously ambitious undertaking.
Yeah, it's a huge challenge in pure mathematics.
But I have to imagine there's more to it than just mathematical satisfaction.
Oh, for sure. It's like we're laying the foundation for a skyscraper.
Okay, I like that analogy.
You might not see the practical applications while you're down in the dirt, but without it.
You can't build anything impressive.
Exactly. And this research could have implications for fields like cryptography,
Ooh, okay, now we're talking.
computer science, maybe even theoretical physics.
So how does understanding these abstract spaces and their generators translate into something tangible like that?
Well, for example, secure communication in cryptography, it often relies on complex mathematical structures, right?
Right, to make sure nobody's eavesdropping.
Exactly. So the more we understand about different types of mathematical spaces,
Including the non-commutative ones.
especially those, the better equipped we are to develop new and more sophisticated encryption methods.
So cracking the code of these non-commutative spaces could lead to uncrackable codes in the real world.
You got it. And that's just one example. Think about computer graphics
Oh, wow, yeah.
or modeling complex systems in physics. A lot of these fields use really sophisticated geometric representations. Who knows what we could achieve by incorporating these non-commutative ideas into those areas, right?
You've definitely got my attention. So how did this paper go about finding these elusive generators?
Okay, so they focused on this powerful concept called descent.
Descent, like going down into something?
Kind of. Imagine you're trying to solve a giant jigsaw puzzle.
Okay, I can picture that.
Descent is like saying, hey, if I can figure out these smaller sections...
You can understand the whole picture.
Exactly.
Yeah.
They applied that same logic to generation in these non-commutative spaces.
So it's a divide and conquer strategy, but for abstract mathematical spaces.
You got it. And here's where it gets even more mind-blowing. They found a way to use what we know about simpler commutative algebra to tackle this non-commutative problem.
Wait, hold on. So they're basically saying, we know how to find generators in these easier commutative spaces, so let's use that knowledge to help us with the more complex non-commutative ones.
You're catching on quick.
Yeah.
They essentially built a bridge between those two worlds using something called the projection formula.
That's wild. It's like they found a secret passageway between two totally separate realms.
That's really cool, and a good example of how mathematicians often work.
Always building on what's already known.
For sure. They build upon existing knowledge, look for those connections and patterns that can lead to new insights.
Now, the paper also mentions these Azumaya Algebras. Do those play into this descent idea at all?
Absolutely. They are a special type of non-commutative structure.
Okay.
And they have some really nice properties that the researchers were able to take advantage of.
So they used those properties, along with this descent strategy, to actually find some generators.
They did. They proved that in a lot of cases, you can actually construct generators for these complex non-commutative spaces just by looking at simpler related spaces.
So it's all about finding those elegant shortcuts, those underlying structures that make everything seem much simpler than it first appeared?
Exactly. That's exactly why this research is so compelling. It's not just about solving one specific problem.
Right, it's bigger than that.
It's about developing new tools and techniques that could have a huge impact on how we approach problems in all areas of math.
And beyond. So this paper, it feels like it's really pushing the boundaries of what we know about these non-commutative spaces.
It really is.
But I'm also getting this feeling like this is just the tip of the iceberg.
Oh, absolutely.
There's so much more out there to explore, right?
That's the thing about math, isn't it? Always more to discover.
So where do we even go from here? What are the big unanswered questions that this research has sparked?
Well, one thing that comes to mind is, this paper focuses on some very specific types of non-commutative spaces.
Right, the ones that are coherent, Noetherian.
Exactly. But what if we could take these ideas, these tools, and apply them to even weirder spaces?
Now you're talking about spaces that would make my head spin.
Maybe. But that's where things get really exciting.
I can only imagine.
Spaces that seem totally bizarre right now, they could hold the keys to unlocking even deeper mathematical secrets.
Well, on that note, I feel like we've done some pretty serious exploring today.
We've covered a lot of ground, that's for sure.
We started with, the very basics of non-commutative algebra, and now we're talking descent, Azumaya algebras, all these amazing concepts.
And don't forget those real-world applications.
Yeah.
Photography, computer science.
Oh, yeah. This stuff has the potential to really change things.
It really does.
And a huge, huge thank you to you for being our guide through this incredible and incredibly complex topic.
Happy to do it. Always a pleasure to nerd out about this stuff.
And to all our listeners out there, we hope this deep dive has maybe sparked your own curiosity.
Yeah, go explore those mathematical mysteries.
Who knows, maybe one of you listening will be the one to unlock the secrets of those even weirder spaces we were just talking about.
Wouldn't that be something?
It sure would. But until next time, keep those brains engaged. Keep asking those big questions.
And we'll see you on the next deep dive.
See you then.
Welcome to another deep dive. Today, we're going to try to step into the world of advanced math.
But don't worry, we'll make sure it's an exciting trip.
We're diving into non-commutative algebra.
And you've given us quite the starting point.
A research paper called Get This, Descent in Generation for Non-Commutative Coherent Algebras over Schemes.
I don't know about you, but that title alone makes me want to grab a coffee and settle in.
It's quite a mouthful, isn't it?
But don't let the jargon scare you.
It's really a fascinating exploration of how mathematicians are trying to break down these complex abstract structures.
Kind of like deciphering an ancient language.
Okay, so before we crack the code of this paper,
Let's start with the basics.
what exactly do we mean by non-commutative algebra.
I get that algebra involves equations and variables.
But where does the non-commutative part come in?
Think about it this way.
In regular algebra, the order in which you add numbers doesn't matter.
2 plus 3 is the same as 3 plus 2, right?
Right.
But in the world of non-commutative algebra,
Things get a bit more rebellious.
it's like suddenly the order in which you arrange objects completely changes the outcome. It's like baking a cake.
If you mix the ingredients in a different order, you might end up with a disaster instead of a delicious treat.
Exactly.
And this added complexity opens up a whole new world of possibilities in mathematics.
It allows us to describe and analyze things that traditional algebra just can't handle.
That's fascinating.
So where does this non-commutative algebra actually show up in the real world?
I mean, besides abstract mathematical papers, of course.
Well, you might be surprised to learn that it pops up in quantum mechanics.
Quantum mechanics.
Now, that's a plot twist I wasn't expecting.
Right.
It turns out that the behavior of those tiny particles like electrons and quarks
Doesn't always follow the nice, predictable rules of everyday algebra.
in the quantum world, things can be in multiple states at once.
And that's where non-commutative algebra comes into play.
So to understand the subatomic world,
We need this whole other level of math.
that's mind-blowing.
Does it have any other applications?
Absolutely.
For example, take a symphony orchestra.
You have all these different instruments playing their parts.
Creating this incredibly complex soundscape,
Well, representation theory
which is closely related to non-commutative algebra.
is like the conductor's score.
It provides a framework for understanding how all those individual parts come together to create the overall harmony.
I'm starting to see the connection.
So non-commutative algebra provides the tools for this kind of deconstruction in the world of mathematics.
Breaking down complex systems into their fundamental components and figuring out how they interact.
Precisely.
It's like having a powerful microscope that allows us to zoom in on the intricate details of mathematical structures.
And uncover their hidden patterns and relationships.
All right, I think I've got a handle on the what and why of non-commutative algebra.
Let's dive into the how.
This research paper you've shared,
What are some of the key ideas it explores?
well, the paper dives into two fascinating concepts.
Descent and generation.
And they're more intuitive than they sound.
Let's say you want to understand how a car engine works.
But staring at the whole thing is overwhelming.
Descent is like breaking that engine down into smaller, more manageable parts.
The pistons, the cylinders, the spark plugs.
Until you understand each piece.
So it's all about making the complex manageable.
You got it.
Now, generation is the next step.
Once you understand those parts, generation helps us see how they fit together to make the whole engine run.
It's like discovering the blueprint or the instructions for building a complex machine from simpler components.
Okay, so if I'm getting this right,
This paper looks at how to apply these ideas
descent and generation,
to these, what did you call them?
non-commutative coherent algebras over schemes.
I'll admit those are still a bit of a mystery to me.
Don't worry, we'll unpack those terms.
Schemes are kind of like blueprints.
But instead of for a building, they're blueprints for these abstract mathematical structures.
And those coherent algebras are like layers of rules or relationships on top of those blueprints.
Imagine the blueprint specifying the shape of a building.
And the coherent algebra dictating how the rooms are connected and used.
Yeah.
It's like the blueprint says, this is where the walls go.
And the coherent algebra says, this is how you arrange the furniture.
Precisely.
And in the case of non-commutative coherent algebras, those rules might not always be straightforward.
They can get a bit, shall we say, unpredictable.
Okay, so we've got our blueprints
Our schemes.
and our rules.
Yeah, coherent algebras.
But this paper,
It's not just describing them right.
they're trying to use descent and generation to uncover something specific about these things.
What is it that they're after?
That's where things get even more intriguing.
They're exploring how these non-commutative coherent algebras behave when we push them forward.
Using a specific kind of mathematical transformation,
Think of it like taking a photograph and zooming in on a specific detail.
pushing forward in mathematics is about focusing on a particular part of these structures.
And seeing how their properties change when viewed through that lens, instead of looking at the whole picture.
They're saying, let's zoom in on this corner and see if the rules still apply.
Exactly.
And what they're finding is that sometimes the rules do change,
And sometimes they don't.
and figuring out why that is.
Well, that's a big part of what this research is all about.
Okay, now I'm hooked.
So how do they even begin to tackle that?
What are some of the tools they use in their mathematical toolbox?
That's where we get to the really cool stuff.
One of the key tools they use is a concept called descendability.
And it's all about figuring out if we can understand the whole by understanding its parts.
It's like trying to solve a giant jigsaw puzzle.
Sometimes it's easier to work on smaller sections and then piece them together.
I love that analogy.
So instead of trying to analyze the entire zoomed-in algebra at once,
They're breaking it down into smaller, more manageable pieces to see if the rules still hold up.
precisely.
And this approach, as you'll see, leads to some pretty remarkable discoveries,
One of the tools they use is something called Azumaya Algebras.
which are like mathematical chameleons.
Mathematical chameleons.
Okay, now you have to explain that one.
I thought we left the animal kingdom behind when we stepped into the world of abstract math.
It does sound a bit strange, doesn't it?
But these Azumaya Algebras are fascinating.
They have this remarkable ability to change their appearance, depending on how you look at them.
It's like they're wearing different disguises.
But underneath, they still have the same essential properties.
Okay, I think I'm starting to get a feel for why these Azumaya Algebras are so useful to the researchers,
It's like they're holding up a prism to these pushed-forward algebras.
revealing hidden structures that we wouldn't be able to see otherwise.
That's a great way to put it.
By viewing these transformed algebras through the lens of Azumaya Algebras.
The researchers can unlock secrets about their behavior and how they change under these mathematical transformations,
It's like having a key to a secret code.
unlocking hidden messages within these mathematical structures.
So using these tools.
Descendability, Azumaya Algebras.
What did the researchers actually discover?
Did their deep dive into these non-commutative coherent algebras yield any surprising results?
What's fascinating is that they found these algebras exhibit a kind of resilience.
A robust...
Bounded.
You mean they don't spiral into something infinitely complicated?
Even when we're putting them through the ringer with all these transformations,
Exactly.
it's like they have a certain inherent structure that prevents them from becoming too chaotic.
Even when we try to push them to their limits.
That's incredible.
It's like they have an internal gyroscope.
Keeping them stable even amidst all the mathematical turbulence.
This robustness that you mentioned.
How do they actually measure that?
I mean, how do you quantify the complexity of a mathematical structure?
That's where another intriguing concept comes into play.
Countable Rouquier dimension.
Think of it like a mathematical ruler for measuring the complexity of these algebraic structures.
So it's a way to say...
This algebra is this complex and this one is that complex.
Exactly. And what the researchers found is that even after being pushed forward...
The countable Rouquier dimension of these algebras often remains within certain limits.
So it's like there's a speed limit for how complex these algebras can become.
No matter how many transformations we throw at them.
You could say that.
And this finding opens up a whole new avenue of inquiry in the field.
It's prompting mathematicians to explore what factors influence this robustness.
And what it tells us about the fundamental nature of these algebraic structures.
This is all so fascinating, but I have to admit my brain is starting to feel a bit full.
Before we move
I
on,
want to make sure I've got all the pieces of this puzzle.
we're exploring how these non-commutative coherent algebras over schemes behave when we push them forward.
Using mathematical transformations.
The researchers are using tools like descendability and Azumaya algebras to break down this complex process,
And what they're finding is that these algebras have a kind of inherent robustness.
which they can measure using something called countable Rouquier dimension.
Did I get that right?
You've got it.
You're picking up the lingo like a natural.
Well, I have the best teacher.
But before I let my ego get too inflated, there's one more thing I wanted to ask about.
Earlier, we touched on prime characteristic.
I have a feeling it's not just about prime numbers.
Yeah. What's the connection to all of this?
You're right to suspect there's more to it.
Prime numbers do play a role, but it's a bit more nuanced than that.
In the world of mathematics, we often work with different number systems.
Not just the ones we use every day.
Some of these systems are based on prime characteristics.
Think of it like this.
Imagine playing a board game with a completely different set of rules.
That's what it's like working in a prime characteristic world,
The rules of arithmetic are a bit different.
leading to some intriguing consequences.
Okay, different rules of the game.
So how does that apply to these non-commutative coherent algebras we've been talking about?
Does it change the way they behave?
It definitely adds another layer of complexity.
You see, working in a prime characteristic setting.
Can sometimes reveal hidden patterns and structures that we might not see otherwise.
It's like looking at a familiar object under a blacklight.
Suddenly you notice details and relationships that were previously invisible.
I'm really starting to see how interconnected all of this is.
The non-commutative part descent and generation, Azumaya Algebras, prime characteristic.
It's like they're all threads in the same intricate tapestry.
That's a beautiful way to put it.
And that's one of the things that makes mathematics so captivating.
It's about exploring these connections, unraveling the hidden patterns and relationships that govern the behavior of everything.
From the subatomic world to the vast expanse of the cosmos.
Speaking of connections,
How does this prime characteristic idea tie back to the research paper?
they weren't just exploring this concept in a vacuum, were they?
Not at all.
They found that by combining the ideas of descent and prime characteristic,
They could gain even deeper insights into the behavior of these non-commutative coherent algebras,
okay, so it's like they're taking the descent approach
breaking down the problem into smaller parts.
and applying it within this prime characteristic world where the rules of the game are a bit different. It's like using a specialized toolkit to unlock secrets that would be inaccessible using traditional methods.
So by combining these different perspectives,
They're able to paint a more complete picture of these complex mathematical objects.
exactly.
And that's what makes this research so compelling.
It's pushing the boundaries of our understanding and revealing new layers of complexity in a field that is already full of surprises.
Well, they've definitely surprised me.
I never would have guessed that something as seemingly abstract as non-commutative algebra could have such far-reaching implications.
And that's the beauty of mathematics.
You never know where it might lead you.
But there's one more intriguing detail from this paper that I think you'll find fascinating.
Okay, you've piqued my curiosity.
What's this one last intriguing detail?
It involves something called the Frobenius morphism.
Now, I know that might sound intimidating, but bear with me.
Okay.
You've got my attention.
Lay it on me.
Imagine you're trying to copy a complex pattern.
Like an intricate mosaic.
The Frobenius morphism is like a special tool that lets you lift certain parts of that pattern
And reproduce them in a slightly different way.
while still preserving some of the original structure. It's like a mathematical photocopier.
But instead of just making a duplicate,
It creates a variation on a theme.
that's a great analogy.
And in this research, they're using this Frobenius morphism
In the context of non-commutative algebra,
to explore how these coherent algebras behave when they're subjected to this kind of lifting process. They're taking these already complex structures,
applying this lifting tool,
this Frobenius morphism.
and seeing what emerges on the other side.
What are they hoping to learn from that?
What they're finding is that even after being lifted by this Frobenius morphism,
These algebras still retain a remarkable degree of order and structure.
it's like they have this inherent ability to withstand these transformations without completely falling apart.
That's
Like they have this internal scaffolding that keeps them standing.
even when they're being twisted and reshaped.
Exactly.
And this discovery has some profound implications for our understanding of how these algebraic structures work.
It suggests that there are deeper, more fundamental principles at play that govern their behavior.
Even in the face of these complex transformations.
This has been an incredible journey.
We've gone from the basics of non-commutative algebra to descent and generation.
From Azumaya Algebras and prime characteristic all the way to the Frobenius morphism.
It's amazing how this one research paper touches on so many different aspects of this field.
It's a testament to the interconnectedness of mathematical ideas.
And it highlights how even highly abstract concepts can have far-reaching implications.
Well, you've definitely opened my eyes to a whole new world of mathematical wonder.
Before we wrap things up, is there a final takeaway you'd like to leave our listeners with?
I think the biggest takeaway is that mathematics is not just about memorizing formulas or solving equations.
It's a journey of discovery.
A quest to unravel the hidden patterns and relationships that govern the universe around us.
Beautifully said.
And who knows what other mysteries and wonders await us in the vast landscape of non-commutative algebra.
I, for one, am eager to find out.
Me too.
It's a field ripe for exploration.
Well, on that note, I think we'll call it a wrap.
Thanks to our expert guide for this incredible deep dive.
And to our listeners, thank you for joining us.
Until next time, keep those minds curious.